Section 3.8 is about Newton's method. Newton's method is a technique for approximating the real zeros of a function using tangent lines to approximate the graph of the function near its x-intercept. What that means is maybe we're given a function that's really hard to find the x-intercept, so we can use Newton's method to approximate where it's at. Maybe, you know, it's not a really easy one. It's a bunch of decimals and it's not an exact number and all that, but we can use Newton's method and get really close to where that zero is going to be. So here's some steps to help you approximate for Newton's method here. Okay, we're going to make an initial guess, and how we make an initial guess is look at a graph. Maybe we have 1 and 2, and this function comes somewhere in between there, but we have no idea what it is. So I'd make a guess, maybe 1.5. So my initial guess, my x1 would be 1.5. That's my initial guess. To figure out what the next one is, we're going to use this equation right here. So to figure out what x2 is, we plug in my x1 here, all right, because 1 plus 1 is 2, right? So that's x2. I plug in my 1 here, and also into the derivative. Okay, and I'll show you more here in a little bit of how that really works. And step 3, the last thing, is to make sure it's as close as we want. So maybe we want to get within like 1/100th of a distance between the actual 0 and what we're approximating. So we want to get within that area, so we just subtract. Maybe my x2 somehow comes out to be 1.499, and I'm within the range that I wanted. All right, and so then we can stop if we're within our range. So we subtract 1.5 and 4, or 1.4999. Okay, and make sure within our range. Okay. If we're not close enough, we just repeat step 2 and find the next one. So here we go. Now I'm going to have to show you on the calculator here. So try to stay with me. This says calculate 3 iterations. Oh, and I skip. Every time we do that step, that x to the n plus 1 equals our x to the n minus the function over the derivative of the function. Okay. Every time we do that step, it's called an iteration. So what we're going to do is we're going to do 3 iterations of Newton's method of this one right here, which is just x squared minus 2. Well, we know our Newton's method is our initial guess, or our guess, or our x all over the y value. So the value of x at that function, also the value of x at the derivatives function, or at the derivative. So what I need to find is I need to find my derivative. F prime of x is going to be just 2x. So when I'm working out my iterations for these, and it says use x equal to 1 as our first iteration, but when I'm working this out, so I'm going to have x to the n minus x squared minus 2 all over 2x. And all I do is for my initial guess, I'm going to plug in, so for x1, I'm going to plug in 1. So to figure out what x2 is, I have to do this. So to figure out what x2 is, I'm going to plug 1 and use 1 as my x to the n, because that's my x to the n. That's my initial guess. Okay, so I'm going to plug 1 minus 1 squared minus 2 all over 2 times 1. When I square 1, I get 1. 1 minus 2 is a negative 1. 2 times 1 is 2. So this inside here became a negative 1/2, cross the line, change the sign. So I get 3/2. I get around 1.5. So x2 is 1.5. To figure out what x3 is, I need to do this again. So to figure out what x3 is, I'm going to take 1.5. So I always take my previous number, 1.5, and I'm going to plug it into the Newton's formula here. So it'll be 1.5 squared minus 2 all over 2 times 1.5. And this is where, 1.5. This is where I'm going to have to use a calculator to show how to do that. So we're going to figure out our x3. Don't let that fool you. We've only done 2 iterations. We actually have to go to x4 to get our 3rd iteration. Let me pull up a graph, or my calculator right here. All right, so we wanted to figure out what x3 was. So it was 1.5 minus parentheses, I believe it was 1.5 squared minus 2, was it? Is that right? Minus 2, yep, minus 2. That's on the top, and then I need to divide it by parentheses 2 times 1.5. So that's all calculator work there. Whoops. So like that. And I get 1.41667, all right? Well, I wanted 3 iterations. We found 2. We plugged 1 in, we got our first one. We plugged 1.5 in, we got our second one. We got to find another iteration, so we need to use our 1.41667. Something that'll help you, I'm not sure if anyone's ever showed you on your calculator, is the store button. See this STO with an arrow? That's the store button. So I'm gonna, when I hit store and then I make it some letter, I'm gonna call it A. What it means is every time I type A in there, it means 1.41667. So I don't have to keep typing out 1.41667 every time I want to plug that in. So if I want to do my next iteration, it's going to be my A, which is 1.41667, minus my value, or minus my A squared, because that was my function, A squared minus 2. And I need to put one more parentheses because we're subtracting the whole thing, divided by 2 times A, which is my 1.41667. Okay, and I'm going to close it. I'm going to get my next iteration, which is 1.41422. All right, and as you notice, these numbers are going to keep getting, if Newton's method is going to work, these numbers are going to keep getting closer and closer to some number, so it's going to get closer and closer to approximation. Notice that we're only about 2 thousandths off right here, and maybe that's all the closer we want to get. If we wanted to get within with 1,000th of a place, we'd have to do it one more time. All right, so that's how Newton's method works there. If Newton's method, if it oscillates, maybe if it doesn't converge to something, notice how this is kind of conversion. It's going towards 1.40, kind of, you know, but it's not. We don't get like a negative and a positive and a negative, or we don't get like 1 and then a -3 and then a 1 and then a -3. As long as it's not doing something crazy like that, Newton's method is going to work. Newton's method can fail. So if you're trying to do this and you get some crazy stuff, you get like a 1 and then a -3, or you get like a 0 and then a -5, and then the next one you go from -5 back to a +5. Something just crazy like that. Newton's method doesn't work then, and then it just doesn't converge and we can't use it. All right. So there's Newton's method. As long as it converges, we'll be okay. And there's Newton's method. And the only difference is in this next example, and I don't have time to show you, is you do your approximations until you're this close. So you subtract your iterations, and if you get within 0.0001, then you can stop. All right. So that's it for Newton's method. We'll see you in class.